my final lecture, basically, and we will have a 2-week break. After that, Professor Pajan will give a couple of lectures, and then some of you will present a seminar. So that's the idea. So let's finish up this, what I meant to say about the system of pipes. So we will look a bit about power law fluids. In a system of pipes. So I will be talking about a more or less simple model regarding power law fluids and consider the flow for a system of pipes. We will not, again, do the matching procedure, etc., which is more or less the same, but we'll focus on, you'll see there are a couple of things regarding the flow that you need to consider when considering the pressure. So that is, in some sense, a novelty here. So, problem settings. So the other ideas are basically very similar to the ones presented for the Newtonian and micropolar case. So this is following a paper by Professor Maržić-Poloka and Pajan in from 2015, so it's, I think, in 2015. Okay, so the settings you more or less know by now, but I will repeat them. They're similar, so epsilon I, some of the notation is a bit different, but so this is a smooth bounded domain. So you have a cross section of the ith pipe. And of course, S epsilon I is basically epsilon Si. So this is a general form. Of course, when you have circular cross sections, then you can obtain, more or less, always obtain some formulas. So explicit expressions, to be more precise. So omega epsilon I will be each pipe. So X is X1I, X star I from R3. So X1I is from 0 to L. X star I is X2I, X3I from S epsilon I. Okay, where of course I is from 1 to some m, and this is posed in some different coordinate systems, possibly. Usually they are the same, but it's not necessary. So different coordinate systems. EJI. So this is 1, 2, 3. Okay, of course, the complete domain will be omega epsilon, which will be the union from 0 to m. Omega epsilon I and omega epsilon 0, which is omega 0. Epsilon 0 will be the small reservoir, the junction. So in a small reservoir. We call it the junction, but the same. So where the pipes omega 0 is a smooth smooth bounded domain containing the origin. Sigma epsilon I will be the ends of the pipe, so Li x star I from R3, so x star I is epsilon Si, I is 1 to m, and the boundary, the lateral boundary basically, will be the boundary of omega epsilon without the ends of the pipe. Okay, so this is more or less what we had before. But now we have a bit of a different system. Okay, so we suppose that the pipe system omega epsilon is filled with a non-Newtonian fluid with viscosity eta obeying the following law. So a class of fluids are quite well modeled by this. Probably Jean knows a lot more than me. So you consider it in this way, viscosity law. So eta of u is me du to r minus 2, where r goes from 1 to infinity, and me is a constant bigger than 0. You can denote this by 1. So this du, of course, as is usual in the notation, is the symmetrized gradient of the viscosity. So 1 over 2 gradient of u plus gradient of u transposed. So this is the symmetrized I think it's 2m here, not sure. So symmetrized gradient of the velocity. Okay, so of course when you have r equals to 2, you have the classical Newtonian model. So this is not so interesting to us. So the equations with regards to this the equations we consider have the following form. So minus me, divergence of du epsilon r minus 2 du epsilon plus gradient p epsilon is 0 in omega epsilon. So this is the equations that we consider, with of course the incompressibility condition in omega epsilon. Of course, as I mentioned, for r equals to 2, you have the classical Stokes system. Okay, so let's make some remarks regarding this. So the first remark would be the following. So this maybe has changed, and maybe Jean knows a bit more about this regarding the existence issues. So this was, at least as far as I know, in 2015 this was correct. So we notice that we have neglected the inertial term. So U epsilon, gradient U epsilon into 1. So this is 2. So this is because the existence and uniqueness for such a system is not completed. So the problem arises when r is close to 1. Is it solved now? Do you know?
Yes, it's basically, yeah, the problem for is the diffusion.
Okay.
So,
but is the
P Stokes, which is what you wrote, there is. It's not that difficult to prove.
Yeah.
Just use the Minty-Browder theorem in the spaces where the divergence of the velocity is 0.
Mm-hmm.
Yes, it's basically this. It's not difficult, but for the P Navier-Stokes, we have the existence but not the uniqueness.
Ah, so it's not complete.
Yes.
Okay. So it's still a problem. It's not completed. Okay, this is enough. Thank you for the completement of the remark. Okay. So regarding the boundary conditions, they are more or less what we have used a lot. So the boundary conditions is U epsilon equals to 0. The lateral boundary, so U epsilon is in the direction E1, and P epsilon is Pi on gamma epsilon I is 120. Okay, so this is the setting of the problem, and let's try to see what happens. It's a bit, of course, different than what you would obtain for classical Stokes system, so let's see the difference. So we call this 432 the power law. I don't know how to write. Say, I think it's like this, flow. Okay, so if I take this conjugate, so r over r minus 1, then I expand in the following way. So U epsilon is given in this way. So ER times UI x1I x star I over epsilon. And we will introduce this, of course, y star I. And you have P epsilon, which is Pi x1I x star I over epsilon plus epsilon Qi x1I okay. So we will repeat this. Of course, you plug into the system and see what happens. So plugging, if we denote this by 4, so plugging 4 into 2, 3, so the system and the boundary conditions after some computation. We obtain the solution in the following form. So UI y star I is VI y star I. So these expressions are of course more complex than the classical Poiseuille. So Pi minus P0 over Li to the R minus 2 P0 minus Pi over Li E1I. Well, this y star is of course from SI. Okay, and this VI is, so we have the general cross section, so this is not determined, but of course if we restrict ourselves to the circular case, we'll obtain the solution in explicit form. So where VI is the solution, of the following. So following problem. So minus me divergence of gradient Vi R minus 2. Gradient Vi is 2R over 2 in SI. And this Vi is 0 on the boundary of SI. So we know this by 6 and this by 5. Okay, and the pressure is given in a very simple form, so it's given in the form, so Pi of x1I is P0 plus Pi minus P0 over Li x1i, where of course x1i is from 0 to Li, and qi is 0. So the term by the epsilon. Okay, so as I mentioned, with regards to this, so remark 2, and case from the applications, let's say, the most usual. So if the pipes are assumed to have a circular, so circular cross sections, namely Si is y from R2, where the absolute value is less than Ri, and Ri, of course, is a constant bigger than 0. Then the problem, so the problem 6. Can be explicitly solved. So you have the following formula. So Vi y star I is 1 over 2 r over 2 minus 1 mi r minus 1 times r. So this is more or less expected from the Poiseuille that you have this form. But you have these powers and some coefficient, some constant in front. Okay, what we'll also need now when we'll consider the Kirchhoff junction rule, you will see why, is the following. So this will be important by a simple integration by parts. We obtain the following. So Vi is the integral of Si, so the mean value, let's say, y star I. So this can be shown that this is mi over 2 to the r over 2, integral Si, gradient Vi to the r, the y star I. So this value is bigger than 0, and this will be important in the following considerations. So this is more or less what is expected. Of course, you have a bit of a different, we'll say, flow that is adapted to the power law. But now there's a bit of a problem with the pressure. So let's look at this. So for free, you have Kirchhoff junction rule. So the problem is the pressure P0 in the junction. Okay. Sorry. So P0 in 5, which was the expression for the power law plus safe law, the velocity, remains undetermined. So we in some way need to determine this. This we haven't done yet, so it remains undetermined. So this is the pressure in the junction omega 0. So first, from 2, you obtain the following. So this is the divergence equation. So equation 7. So 0 is equal to the sum of 1 to m, integral over the ends of the pipe, of the system of the pipes, u epsilon I times E1. Okay, with a simple change of variables and taking into account what is u epsilon I, you obtain minus epsilon r plus 2, sum I is 1 to m, so this value Vi, and then you have, erase this. So you have Pi minus P0 over Li to the r minus 2, and then Pi minus P0 over Li. Okay, so we have this, and you introduce the following value. So introduce Hi, which is equal to Vi r minus 2 Vi. So this is bigger than 0 by remark 3. So it can be shown that from here we have the following. So the absolute value of H1 of r minus 2 Hi is equal to Vi. Okay, there's a lot of computation beside all this, but I'm just outlining the ideas. Okay, so why is this important? Well, now you obtain from 7. So from this condition, you obtain that the sum of 1 to m, Hi over Li, Pi minus P0, r minus 2, Hi over Li, Pi minus P0 is equal to 0. So this is formula 8. Now, if we consider, you always want to look at the case where you can compute something explicitly, so let's see if we can. So we consider a pipe system where m is equal to 2. So we have 2 pipes. So with only 2 pipes, so connected at the junction. so this m is equal to 2, we can then so explicitly compute so the junction pressure P0. So in this case it's not so hard, as you can see. Of course you want your expressions and your result to be as general as possible. This is a good remark. So P0, so for m equals 2, we obtain from 8 the following: H1 over L1, P1 minus P0, R minus 2, so H1 over L1, P1 minus P0 is equal to minus H2 over L2, P2 minus P0, R minus 2, H2 over L2, P2 minus P0. Okay, so the above equality is going to be fulfilled if and only if let's write here H1 over L1. So H1 over L1 Pi minus P0 is exactly equal to minus H2 over L2 P2 minus P0. Okay, this is obvious. So in this case you can now easily obtain the expression for P0. So it follows that P0 is H1 over L1 P1 plus, so it's a nice expression, H2 over L2 P2, and here you have H1 over L1 H2 over L2, where we introduce this notation. So Hi was given by the following. Okay, so this is the Kirchhoff's law for m equals 2. But we will want to consider the general case, of course. Before that, let's just make a remark. So, remark 4. We have the following. So, if we have again two circular pipes, so like in a remark, I guess it was 2. We get the following expression. So P0 is P1 over L1, R1 free R minus 2 plus P2 over L2, R2 free R minus 2, 1 over L1, R1 free R minus 2 plus 1 over L2, R2 free R minus 2. So, okay, so you obtain this explicitly. Why we consider this specifically? Well, if you have a more general setting, where of course you want to have more than 2 pipes, then you have to be a bit more, get more technical, to say the least. So in the general settings, so this is M, which is bigger than 2. So we cannot explicitly compute the junction pressure. P0 from 8. Of course, when you're in general setting, it's impossible. However, and this is in some sense a novelty, maybe, so we can show that so P0 is of course implicitly uniquely determined. By 8. So let's see in what way. So you will need to use some inequalities which you can get from the literature. But let's first see what we have. So you have this implicit function f P1, P2 up to Pm. So these are given pressures. And you have this P0, which is making your problems. So define this in this way. You have this sum Hi over Li, Pi minus P0, R minus 2, Hi over Li, Pi minus P0 is equal to 0. Okay, so what is the basic idea? Well, for given pressures, P1 to Pm, we consider the following function. So a function gt where this single variable function is given in this way, so P1 to Pm t. Okay, what you want to show is that this function has a unique P0 such that g of P0 is equal to 0. So, and then you have what you need. So, first of all, we can note the following. So, note that the limit when t goes to infinity of gt is minus infinity. And the limit when t goes to minus sorry. Check. I think the first goes to infinity and the second to minus. Okay. This is plus. Just to be sure. Okay, t goes to minus infinity. G of t is plus infinity. So we will show in the following that this function g is basically a strictly decreasing function. So in order to prove the existence. So this is our claim. So we haven't worked much with these kinds of problems where we have some inequalities or equalities, but this also appears sometime. So the t is a strictly decreasing function. So if we prove this and you have this asymptotic behavior, then we conclude that there exists a unique p0 such that g of p0 is equal to 0, and you have your p0 uniquely determined by this implicit equation. So we use the following inequalities. So these inequalities are important and they have been proven out in a paper by Sandri in 1993. So this is from some previous work. So we have two cases, and this R is bigger than 2. So this is also called a dilatant fluid. So C1 B R minus 2 plus A R minus 2 B minus A squared. I'll write down. So we have B R minus 2B minus A R minus 2 absolute value, A B minus A. Okay. And for the case when R is between 1 and 2, you have this pseudoplastic fluids. So here you have C2 B minus A squared over B2 minus R. So you have quite different inequality, 2 minus R. So this is less than equal to B R minus 2 B minus A R minus 2A B minus A. And we denote these two inequalities by 9. So where these A and B, let me just check, are generally from Rn, C1, C2 is a constant bigger than 0. Okay, so these inequalities were shown by Sandri. So it's a paper, I think, in French. So it's a paper in it's really a long name. So it's mathematical modeling and numerical analysis. Okay, let's just write this. So mathematical modeling and numerical analysis. So it's from 1993. Okay, so it was proven then. And when you have these two inequalities, you can check in the paper for, it's a bit of computation, not too much, but it's good for an exercise. So in the first case, when okay, this was basically the case when r is bigger than 2, the conjugate is bigger than 2. Then you have t minus s, g of t minus g of s. So if we show that this is less than or equal to 0, then you have a strictly decreasing functions, which is more or less obvious. So by 9.1, we have that this is less or equal to minus c1 sum from 1 to m vi over li times, so you have vi minus t over li r minus 2 plus pi minus s over li s minus t squared. So if you remembered, it was important that this value will be bigger than 0, and then this will be less than equal to 0. Okay. So for any st in R. So of course then it's easy to check that if t is what less than or less than equal to s, then g of t is bigger than g of s. So you have g is strictly decreasing function. Okay, more or less similar for the second case, but let's write it down. So in the second case, you have this conjugate is from 1 to 2. So you have a similar equation, more or less. T minus s g of t minus g of s. From the second equation, you obtain the following: minus c2 sum 1 to m. So we have vi over li. So this is 1 over pi minus t over li. 2 minus r plus pi minus s over li. 2 minus r. So using the same arguments, you also obtain that g is strictly decreasing function in both cases. So g is a strictly decreasing function. So you can conclude that, if you remember where we started from, that there exists a unique P0 from R such that g of P0 is equal to 0, and this P0 is the pressure at the junction. So it's uniquely determined. So the idea was to use this bit of a different approach and use these corresponding inequalities with these powers in order to obtain, at least implicitly, this existence and uniqueness. Okay, so I wanted to just write down the idea for the rest. Is basically very, very similar. So this is the main novelty. So let's just comment a bit. So regarding the interior layer correction, of course, again, you have the corresponding Leroy's problem, but I will write it down. And more or less the same approach as before. So the construction corrector in the interior layer. So G epsilon is omega 0 union with 1 to m G epsilon I, and G epsilon I is x1I, x star I. Of course, if you remember that this was the part up until minus d, what was it, epsilon ln epsilon, right? So this construction goes in a similar way. As in 4.1 and 4.2. Let me just write down the problem. So you have the following. So we have the following Leary's problem. So minus me divergence of dv or minus 2 dv plus gradient pi is 0 and g infinity. Divergence v is 0 and g infinity. V equals to 0 on the border of g infinity. And you have the asymptotic condition. So the limit of v is ui in omega epsilon, omega infinity I. So these are the notation as before. I will not write it down again. But this is here, of course, the power law Poisson flow, Poisson velocity. So this problem 10 was addressed, so it has a unique solution which is exponentially decaying. So the existence, but not always. So the existence uniqueness and exponential decay of the solution of 10 for r is bigger than 2. So this is the dilatant fluid, can be found in Professor Maršić-Poloka. So it's called non-Newtonian flow through unbounded channels and pipes. So it's mathematical models and methods in applied sciences from 2000. So this was proven there for r bigger than 2. In the case when r is from 1 to 2, at least in the time of writing of the paper, there was no known results. I don't know if, Jean, you know if this has been solved for r between 1 or 2. Have you seen this Leary's problem?
I saw the papers. The one from them not prove that the decay is exponential, it proves just decay.
Okay.
And the other one
so probably maybe there is someone who proved it in the meantime, but let's just no known result in the time of the writing, in time of publication. Let's write like this. Okay, and of course the construction. Of the asymptotic approximation. Can now be done for r bigger than 2, so can be done for r bigger than 2 along so with the corresponding error estimate. Okay, so this is not so hard. You can check in the paper if you want to know more. So this is basically an overview of the papers I wanted to talk. So we talked about, from the beginning, okay, we had some introduction, then we had some talks about flows in straight pipes, more or less micropolar, some flows in curved pipes, so classical curved pipes or helicoidal, and then a system of twin pipes. So this is some, let's say, basic overview of the domains that are more or less classical and interesting, of course, from the practical point of view. Of course, a number of problems arise when you do something with the boundary. So you can have a smooth perturbation of the boundary, or it can be some other way. So it can be highly oscillating boundary, which more or less is what Jean works with. So there's a number of problems that can arise, of course, in the different systems. So I worked here with generalization, more or less, of the Navier-Stokes, so the micropolar system of equations, which has this coupling that needs to be dealt with and has some new effects that you can consider. But of course, there's a lot of more problems that can be done, but this is like a basic overview of these asymptotic techniques, let's say. Okay, so we will now have a 2-week break. Jean will be leaving for Brazil, but maybe he will follow us online. Professor Pajanin will continue on the 12th of May. I think he told me there will be some talks about flows with porous boundaries. So this is quite a different approach. Okay, so this is it. Thank you for watching, if anybody was or will be watching, and goodbye.